Let's work on some numbers and find a derivation of the relationship between thermodynamics and electrochemistry that we are studying now. If we think about voltage or potential, it has to do with the same thing we talked about in the thermochemistry unit, potential energy. When two items are at positions opposite each other, in favor or against the pull of a fundamental force, we say that those items have a potential energy. In this case, we're talking about the energy that would be required to move a charge between 2 points. So if we talk about units of energy per charge, that would be joules per charge, which is coulombs. And that is essentially what a volt is. It's a joule of energy per coulomb of charge. We know that one single electron has a charge of negative 1.6022 times 10 to the minus 19 coulombs. We normally don't talk about those kind of units because in chemistry, all we deal with is protons and electrons, and we just ascribe charges of +1 and -1 to them. But the real unit of charge is the coulomb. So since many of the transactions that we talk about in chemistry happen with more than one electron, let's say what would be 1 mole of electrons? Well, that would be minus 1.022 times 10 to the minus 19 coulombs, right? Times Avogadro's number, 6.022 times 10 to the 23rd. And that would be essentially electrons per mole. And this would be coulombs per electron. So those will cancel out. And we're going to say, for the sake of illustration, let's go ahead and say that this is going to be minus 96,484 coulombs per mole of electron. And because at this point, we really are not going to be concerned with whether the charge is negative or positive, we're going to say that this is going to be called the Faraday constant. F, and we're going to say it's 96,484 coulombs per mole of electrons. And we're going to call that a constant. Now, remember that when we talk about electrochemistry, we're interested in electrochemical processes. We're interested in what kind of energy we can derive from a redox reaction, right? So in this case, what we're interested in is what is the useful energy that we can generate, right? So what is the maximum work that we could generate in a process? Maximum work that we can obtain. Well, essentially, we're talking energy. Now, we are going to say the following. Number one, it would be, like we said, how many charges are we going to be able to move? And what is the potential? In other words, what is the energy that would be required to move those charges? So this will be the potential here. Now, because our system is the redox reaction, because our system is the one performing the work, we put a negative sign in here, right? That is indicative that this is, by our system. You remember the conventions that we had in thermochemistry about the signs of directions of energy. Well, what is the maximum work that we can obtain? Essentially, that is the total useful energy, the free energy, which is delta G. What is the charge that we're talking about? Well, it would be in any redox reaction, there's a number of moles of electrons that we transfer. So this would be n moles of electrons times the coulombs per mole, which is Faraday constant. And this would be times the potential for this reaction, which would be the potential of the cell. So let's make sure that the units really add up here, okay? Let's look at the units. N would be the moles of electrons, right? Faraday would be the coulombs per mole of electrons. And the potential would be in volts. But if you look at this equation that we had here, you can see that you can express volts as joules per coulomb. And so, as you can see, moles of electrons cancel out, coulombs cancel out, and you have essentially units of energy. So if I were to do a standard cell, I can take this equation I just derived, delta G equals minus N F times the potential. And for a standard cell, and remember when we say a standard cell, we mean these are conditions under which any electrolytes or ions are in 1 molar concentrations. Temperature is expected to be 25 degrees Celsius. If we're talking gases, they would be at 1 atmosphere of pressure. So for a standard cell, that would be delta G naught, the standard free energy, minus NF times the standard potential of the cell, which we have already discussed. You calculate by taking the potential at the cathode minus the potential at the anode. So notice that if the potential for this cell is a positive number, then delta G naught is negative. In other words, in the standard state, this would be spontaneous. Okay, so what we're going to do now is we're going to look at this equation we derived, and we're going to do one more connection, and that is, let's connect now the free energy change with the potential and with the equilibrium constant. So in terms of spontaneity, the derivation is going to take us to this equation here that says that delta G is minus N times F times the potential of the cell. In this case, N represents the number of moles of electrons being transferred in the reaction, and F is Faraday's constant, which is the charge per mole of electrons. Obviously, if we were to do this experiment under standard conditions, delta G would be delta G naught, and of course the potential of the cell would be the standard cell potential. We can use for Faraday's, sometimes some authors like to round it up to 96,500 coulombs per mole, which is the same as saying joules per volt per mole, given the relationship between charge, voltage, and energy. We can use either set of units depending on what other units we're going to try to cancel. Okay, In our previous unit, we derived an expression for delta G naught, in other words, the standard free energy change in terms of the equilibrium constant, minus RT times the natural log of the equilibrium constant. And now we have a second expression here where we're including the voltage of this cell. So let's say that we take these guys here and we rearrange this equation here. So let's say that the voltage of the cell is going to be RT divided by NF times the log of K. I just rearranged the equation that I had there. Most of these things are constants, and most of the time, these values are given at 25 degrees Celsius. So let's go ahead and substitute what we know. We know that R, the gas constant, expressed in units of energy, is 8.314 joules per Kelvin per mole. Let's say we're going to do this at 25 degrees Celsius, which is 298 Kelvin. We have a value here for the Faraday constant. I'm going to use the units that are energy per volt per mole. And the reason for that is simply so I can cancel things out, times the log of K. All right, let me give you a few moments to write that down. And now let's see how these things cancel. Okay, so joules will cancel out with joules. Per Kelvin will cancel out with Kelvin. Per moles will cancel out per moles. Excuse me. And the only unit left standing is the voltage, which flips up. And we end up with this equation here, which is perfectly fine for you to use, all right? It's perfectly fine to use this. As long as we are working at 25 degrees Celsius, you can use this expression here. As a matter of fact, if you want, excuse me for a moment. If you want, we can do this in base 10 logarithms. You can convert between the natural logarithm and the base 10 logarithm. So you're welcome to use either one of these expressions. Notice that in this expression, the only thing we need to fit in is the number of moles of electrons being transferred. And then decide if we're going to use the natural logarithm or the base 10 logarithm. Now here is what is very interesting. In the previous unit, we encountered a relationship between the free energy change and the equilibrium constant. Now we have a relationship between the equilibrium constant and the potential of the cell. And of course, here above, we had a connection between the potential of the cell and the free energy change. So we can build a triangular set of connections here between delta G, the potential of the cell, and the equilibrium constant. And in between those, you can see the equations that connect them. If I were you, probably what I would do is I would take that bottom figure, that triangle, and put it as part of my cheat sheet for the future, because it has pretty much all the formulas that we need for the moment. Notice that everything here is in terms of standard states. This is the standard cell potential, the standard free energy change, the equilibrium constant. We're going to play with these factors later on a little bit, all right? So if we go back to a table that we did before, now that we know that there's this connection between these three expressions here, we can amplify our table where we connect delta G, K, and the potential of the cells. Remember that according to the second law, for a process to be spontaneous in the direction written, delta G has to be negative. Again, this is for the standard state. A negative delta G means that in order to keep that minus RT log K negative, the log of K has to be a positive number. In other words, K has to be bigger than 1. And at the same time, because the expression on the far right, minus NFE, is negative already, we had to keep the voltage positive. Any one of those represents a reaction under standard state conditions that favors the forward direction, the formation of products. Delta G naught being 0 is the same as K being 1. It's the same as the potential being 0, which means that you have a equation where both reactants and products are equally favored. And of course, a positive delta G goes with a value of K that's less than 1, or a negative potential, which means the reaction is not spontaneous in the direction written. And so the direction favored will be the formation of reactants. All right. So time to do some math. So what would be the equilibrium constant for the following reaction at 25 degrees Celsius? I have iron 2 reacting with silver to give me iron and silver ions. Remember, this is the equation we're going to be using. 25 degrees Celsius, R is constant, F is a constant. So the only variables here will be the potential, the number of electrons, and the equilibrium constant. Okay, so let's go ahead and break these up. So we can see that the oxidation reaction in this case, what would be happening at the anode would be silver turning to silver ions. And because we have 2 of them here, we're going to have 2 electrons being produced. Let's see what is the potential for that is 0.80 volts. Remember, this is the potential for the reduction direction. In other words, not the reaction we're showing right now, but the one where silver ions would be reduced into silver. Okay, don't forget that. This is the potential at the anode. The reduction at the cathode would involve then iron 2 ions getting electrons to become iron atoms. And the potential for that is at the table. You're going to find it as negative 0.45. Since we already had the equation balanced, we can see that already the electrons are going to balance out. So when we add them up, it'll cancel. So, but that's important is that according to our equation for the potential of the cell, we need a value for N, the number of moles of electrons being transferred, and that is 2. And now we can add these up. Remember that we can do one of 2 things. We can express the potentials as plus or minus the actual reduction potential, or we can simply say that the potential of the cell will be the cathode minus the anode. Here the cathode is minus 0.45 minus the anode at 0.80. That gives you negative 1.5 volts. At this point, looking at that voltage, what does that tell you about the spontaneity of this reaction? That's right, it's non-spontaneous, right? Because we said that at least in standard state conditions, if the potential is negative, that means the reaction is not spontaneous in that direction. What that means, therefore, is that we expect that when we solve for the value of K, K should be less than 1. It should be a value less than 1. The hint there is we're trying to convert silver into silver ions, right? We know that silver is a precious metal. It resists oxidation. So it was not very likely that this reaction was going to go spontaneously because there's very few things that can be used to actually dissolve silver, in other words, oxidize it. So let's take our equation that we have up there and let's rearrange it. So K should be E to the potential times N divided by 0.0257 per volts. I just took, again, just in case you got kind of a little confused there, all I did was I took this equation that we have here and I just basically rearranged it. All right, I just rearranged it so that I can put the numbers in. We have the standard voltage of the cell. We have the number of moles of electrons that have been added. We're going to plug those numbers in there. So this is going to be minus 1.25 volts times 2 divided by 0.0257. Of course, the volts will cancel out because we don't have unit when we calculate equilibrium constants. Put the numbers in your calculator. Again, don't forget to try to practice a lot. How does your calculator work? How do you put numbers in? How do you make these calculations? Survey says 5.67 times 10 to the negative 23. As we predicted, this should be less than 1 because we knew from the value of the potential being negative that this was not going to be a spontaneous reaction, and therefore the equilibrium would favor the reactants side.